Good afternoon.
Good afternoon, everyone. This session is for paper presentations. 4 research scholars will deliver their lecture, will present their paper. So this session will be conducted by Dr. Chanchal Gorai, IQAC coordinator and associate professor of Department of Mathematics. I am requesting Dr. Chanchal Gorai to take duty for this session. Dr. Chanchal Gorai.
Thank you, Dr. Sujoy Naik. Now, in this session, there are 4 speakers. Presentation time for each speaker is 20 minutes. Of this is Dr. Tonoy Debnath, Research Associate, Indian Association for the Cultivation of Science, Jadavpur. His title of this paper is Endohedral Metafluorescence EMF Properties, Stability and Reactivity. I welcome Dr. Debnath to uh, present his paper now. Dr. Debnath.
Thank you, sir. Thank you all. Am I audible to all, sir?
Yes, yes.
Okay. Thank you for giving me the opportunity to deliver my research work on international webinar on mathematical theory of atoms and molecules, organized by Department of Mathematics, Nagar Day College. So I am going to present my research work now. So the title of my research work is Endohedral Metallofluorescence. It is also called the EMF and its properties, stability, and reactivity. Myself, Dr. Tonoy Debnath, currently working as a research associate in Indian Association for the Cultivation of Science. Now, we all know about the fullerene, that is the C60 icosahedral C60 fullerene. Now, this icosahedral symmetry takes a very much importance. See, here the C60 have contained 60 carbons. So naturally the question arises, theoretically we can design lots of C60 isomers, but why only one isomer exists? Now, if we take this question and start to answer this question from the sketches, then we can find that to design a fullerene or any spherical geometry, we can take trigonal, different type of trigonal, tetragonal, pentagon, hexagon, or septagon, or greater than that faces, and these are the corresponding geometries. And now, as here carbon are bonded to form the fullerene, so due to angle constraint, we can reject it trigonal and octagonal or greater than octagonal surfaces, and the rest can form the fullerene complexes. Now, among these four faces, these two, this is the tetragon and the septagon, these two, when these two form the fullerene, these are called non-classical fullerene. And when 5-membered and 6-membered form fullerene, they are called classical fullerene. Now, between these two, non-classical and classical, the development of classical fullerenes is very much on the in the abstraction zone of the researcher, but the development of non-classical fullerene is not so much developed, and in my lecture I am mainly focused on the classical fullerenes. Now, these classical fullerenes are mainly two types. One is IPR fullerene, where either two 6-member rings are fused, or one 6-membered and one 5-member rings are fused. And another is non-IPR fullerene, where two 5-member rings are fused. This IPR is called isogonal pentagonal rule, where it is articulated that these 6-6 and 6-5 fusings are capable of producing the fullerenes, but these 5-5 fusings cannot capable to produce the fullerene. Now, below the C60, there are no sphere or there are no fullerenes which can form these 6-6 or 6-5 type fusings. So we don't get any type of fullerene below C60. For C60, we get only one IPR fullerene, and that is the icosahedral fullerene. And see, there are another 1811 fullerenes which are non-IPR type, and actually in practical they does not exist due to there at least one 5-5 ring exists. And for other case also, you see the numbers, and you see that for IPR fullerene the number is very much less, whereas for non-IPR the numbers are very much high. Now, this number actually depends on the number of carbon on the fullerene, and it depends on the n to the power 9. Now, some basic theorem to construct the fullerene. First is n minus e plus h equals to 2. These are the Euler's theorems, and from that we actually this is a completely basic theorem to construct the fullerene. And n is the vertices, e is the edges, and h is the faces. Here we can see that this degree of nu, this is equals to 3, and actually this is called here one carbon is bonded with the 3 neighboring carbon. That is where the value of degree v equals to 3, and from that we can predict the geometry, and where we get that h6 equals to n minus 20 by 2, and from that we can predict that n3n equals to c20 plus f6. And this is a basic rule to construct the fullerene. And different type of fullerene software, fullerene generator software, these theorems are very much important. And this is the corresponding geometry, and this is the corresponding 2D geometry of the fullerene. And actually, in the my next slide, we are discussing about this fullerene and endogenous fullerene. Now, I am basically a computational chemist, and I am basically to the simulations, and this is how the simulation is going on. First, we take the input geometry, which is not optimized. Then we run different type of computational software, optimizing software, and these are the corresponding, the animation is the simulation, and after we get the optimized geometry. This is the optimized geometry of the C60 fullerene, and we take the Schrodinger equation to optimize this fullerene. We all know the corresponding Schrodinger equation, so we don't discuss that. Now the optimization process is first we get corresponding, we take a psi gauge and we apply Hamilton operator and we get the E proved value, but always E proved is greater than E0 from the variation theorem, and from this the iteration is going on and until E iteration equals to E0, and ultimately we get corresponding psi of value which is correspond to the optimized geometry of the compound and which is further verified by the experimental result. This is the density function theory. We don't elaborate this. That due to fast and accurate value it gives, we take the DFT and we run all the optimization calculations. These are the corresponding computational methods and corresponding basis sets, and the software as CAG, which is actually fullerene generator software. Apart from that, we use Gaussian, Games, and Orca to optimize the fullerene, and the other softwares are for calculation of rate and corresponding topology of the fullerene. Now, further stability. This is the revert of missing non-IPR fullerenes. Here, by exo modification and endo modification as well as doping, we can stabilize the non-IPR fullerenes. See here, the exo modification means we have bonded some complex with the carbons. In endo modification, we can encapsulate it, different types of atoms, molecular cluster inside the fullerenes, and in the doping, some carbons molecule are replaced or substituted by the other molecules. Here we have concentrated on the endohedral fullerenes, and here encapsulation of atoms, molecules, and cluster inside the non-IPR as well as IPR fullerenes part of the stability, reactivity, and characteristics of the fullerenes. Now the fullerene chemistry. Here we are going to observe the encapsulation ability of the different sizes of the fullerenes and their properties, enhancement of reactivity of endohedral fullerenes as well as cationic fullerenes, and stabilize the non-existent fullerenes through endo, exo, and dual modification. Now, the first work is based on the LIS at the rate of Cn type of fullerene, where we take N equals to 20 to 60 and we encapsulate lithium one by one. Now, these are the optimized geometry of the lithium encapsulated C20, C26, C30, and C36. We have observed that with the increase of the cavity, the binding energy increases, and for C30 and C36, the binding energy becomes maximum, and after that, the binding energy decreases, and for C60, the binding energy becomes 40 kilocalorie per mole. Here, we have also found that with the increase of the cavity size, the encapsulated lithium placed in the side of the fullerene cavity, whereas for lower small fullerene, it placed in the center of the cavity. Now, these are the multiple encapsulated lithium inside the C60. We have optimized different type of lithium encapsulated C60 from Li2 to Li9, and we have observed that for Li4, the binding energy is maximum. It means we can encapsulate up to 4 lithium inside the C60, but the binding energy is negative up to N equals to 9, which means we can, it is difficult, but we can, there is a possibility to encapsulate 9 lithium inside the C60 cavity. This is the deformation energy. Deformation energy means after encapsulating lithium, how the fullerene surface is perturbed. This is called the deformation energy, and we observe that up to N equals to 4, that is this one, the perturbation is not so much. When after that the perturbation is steeply increases, so it means up to N equals to 4, it remains stable. Now, for C20, we can encapsulate maximum 1 lithium inside the C20. For C32, it is N equals to 2. For C42, it is N equals to 4. And for C60, it is N equals to 9. So these are the corresponding stability of the LIN at the C8. Now the geometrical parameter, we also observe that, see, this is the C equals to 4. The CC bond distance not elongated very much, but after that, it is sharp. So it means, it also indicates that the up to C4, the perturbation is not so much observed. Now, this is the other cases where the CLI and LI has also been observed, and it is quite consistent with the experimental results previously reported. Now, these are the population charges. It's a charge of the fluorine surfaces, and we also calculate that. We don't discuss here. Now, the summary. Here we observe that maximum limit of encapsulation of atom inside the cavity increases with the cavity size. Now, for C60, we can encapsulate 4 lithium inside C60 with ease, but it can be up to n equals to 9. Now, here is the important factor is that enthalpy is the stabilizing factor, whereas entropy is the destabilizing factor to encapsulate the fluorine. Now, for here the cluster inside the LIN cluster inside the fluorine take a perfect geometry, and for lower fluorine the banding value is not so much, and while it's encapsulating, the fluorine surface become negative, and the lithium cluster are become positive. Now, the second work is on the reactivity. Reactivity means here we take the fluorine. We said that there are two types of bond. One is 6-6 and one is 6-5. So here two types of bond is formed. One is 6-6 double bond and another is 6-5 double bond. Now, to observe the reactivity, we have considered 3 fundamental reactions: hydrogenation, hydrolysis, and Diels-Alder. And we take the reagent ammonia borate, double water, and butadiene. And the corresponding fluorines and fluorine derivatives are normal C60, Li plus encapsulate C60, Mg2 plus encapsulate C60, and C60 plus. Now, for hydrogenation, this is the animation of hydrogenation process. See, the 2 hydrogen is abstracted from ammonia borane to fluorine, and for other fluorine cases also, we have observed the same process. And yeah, for lithium encapsulated fluorine also we have observed similar things, and the corresponding barrier we have observed that. See, while for normal fluorine the barrier height is 17.4 kilocalorie per mole, whereas when we encapsulate the Li plus, the barrier height decreases about 3 kilocalorie per mole. For 6-5 hydrogenation also, the barrier height is significantly decreases. Now, for hydrolysis, this is the hydrolysis process where we observe the double water hydrolysis, and this is the mechanism of the hydrolysis process this is the corresponding animation. And here also, when we encapsulated Li plus, the reactivity increases as the barrier height decreases from 30.5 to 23.8, and for 6-5 also it becomes 39.8 to 32.4 kilocalorie per mole, which means that on encapsulating lithium plus inside the fluorine, the reactivity increases. Now, for Diels-Alder reaction also, this is the mechanism of the Diels-Alder reaction, and this is the corresponding computational optimization process. And here also, the barrier height is sharply decreases when we encapsulate lithium plus. It means, and this is the corresponding all the optimization values and corresponding barrier height values and corresponding graph. See that from C60 to Li plus C60 to Mg2 plus C60 to catatomic C60, the barrier height sharply decreases, and the bond selectivity also gone. It means that by encapsulating, yes sir. Okay, sir. So on encapsulating monocation to dication, the barrier height sharply decreases, and for C60 plus, it becomes very much lower. Means for C60 plus, here the reactivity is most. So these are the from distortion energy, local atomicity, and homoluminosity. We have further analyzed the reactivity, and after all, we get that when we encapsulate monocation to dication, the reactivity increases, and the reactivity is maximum for cationic C60. Now, these are the dual stability. So, first one is this one is the external modification through which the fluorine can be stabilized, and these are the end-radial modification. See the encapsulation of two metal inside the fluorine. These are end-radial modifications through which the fluorine can be stabilized. So, in my recent work, I have in my recent work, I have taken dual stability where environmental modification is uh, considered in a particular fullerene, and we observe that the enhancement of stability is very much higher than the simple extrahedral or endohedral fullerene. So here we are already in the work in the dual stability process, and through this, the non-IPR fullerenes, that is the which are not stable or not practically synthesized at all, we can actually stabilize the fullerenes, non-IPR fullerenes, and we can further explore the properties and reactivities of the corresponding fullerenes. So thank you. I am very much thankful to my supervisor, Professor Abhijit Kumar Das, ISS, and my mentor as well as my collaborator, Professor Jayanta Kumar Saha, Ali University. Thank you all for giving the attention in my lecture. Thank
This paper is now open for discussion. If you have any questions, you can ask the speaker. I now invite the participant. If you have any question, you can please ask. I think there is no question in this regard, but I have a question to Dr.
you.
Devnath, that why you have not used C32 in place of C60?
Actually, so C60 is experimentally synthesizable, and C32 is a computationally verified optimal geometry. We have also taken C32 in our case C. When we observe the properties, then we take the C32, and the corresponding barrier is, see, the first one I tell there, one minute.
Okay.
See.
Okay. Achha, since there is no other questions, I thank Dr. Devnath from the behalf of Netaji Nagar Day College, and hope that we will meet again like similar type of conference or like seminar, etc. Thank you very much.
Thank you.
Okay.
Thank you. Thank you.
Now I invite Sri Anjan Sadhu Khan. He is present. Anjan Sadhu Khan, who is the Assistant Professor of Physics, Adams University, New Town. His title of the paper is Quantum Phase Transition of Two Electron System. Sri Sadhu Khan, please. Oh, there is a problem.
Hello.
Hello.
Am I?
Hello. Hello, Mr. Sadhu Khan.
Yeah. Am I audible now?
Yes. Now you are audible. So
Okay.
you can start to make the paper presentation.
Okay, first of all, I want to
Uh,
thank the organizer for organizing this kind of events, and thank you for giving me the opportunity to present our research work in the international webinar on mathematical theory of atoms
mm,
and molecules 2020. Let me share my screen. Okay, is the screen is visible to all of you?
yes, yes.
Okay, so good afternoon, everyone. Today I'm going to present our research work, and the title of the talk is Quantum Phase Transition of Two Electron System. And the outline of the talk is like this. We will start with classical phase transition, then we will discuss about quantum phase transition, then we will discuss about the outcomes of our recent project. So first of all, let me start with classical phase transition. Whenever we hear this term phase transition, the most common example that comes in our mind is water boiling to steam or water freezes to ice. Basically, the nature is abundance with phase transitions. Our universe is also thought to have passed through several phase transition as the high temperature plasma formed by Big Bang cooled to form the world as we know today. Basically, phase transition of any system is driven by the change in the thermal energy or randomness of the constituent particles of the system. But what will happen if the temperature of the system is at comes to absolute zero temperature? In that case, basically at absolute zero temperature, the system boils down to the most ordered configuration. And as we all know, that this is the first experimental observation of Bose-Einstein condensate, where here the velocity distribution of gaseous rubidium atom has been shown at temperatures very close to the absolute zero temperature, which indicates that the atoms slow down and their energy decreases, and at a temperature very close to the absolute zero temperature, the atoms collectively forms a different state of matter. But however, at absolute zero temperature, there exists a non-zero motion due to the Heisenberg uncertainty principle, which is also known as the quantum fluctuation. And this non-zero motion can be tuned by some non-thermal parameter in the Hamiltonian of the system. Now, like the critical temperature in case of classical phase transition, for a certain value of the parameter in the Hamiltonian, the bound state of the quantum system changes fundamentally, which is referred as the quantum phase transition. And how we can relate quantum phase transition with atomic system? Well, in the year of 1996, a seminal work by Serra and Kias, they proposed that the symmetry breaking in the electronic structure configuration can be considered as the signature of quantum phase transition in an atomic system in its ground state. Not only that, uh, they had shown that the nuclear charge of a n electron system can be considered as the tuning parameter of the Hamiltonian of the system, and moreover, they have proposed a complete mapping between the critical phenomena of quantum domain and statistical domain of phase transition, where the nuclear charge is playing the role of temperature, and the ground state energy of the quantum system is playing the role of free energy. And there also exists a limiting value of z called stability limit zc of the system as critical point or critical temperature, as we know in case of thermodynamic system or statistical system. Now, the critical nuclear charge is the minimum charge required for an atomic system to have at least one bound state. If the system possesses a nuclear charge less than Zc, that means critical nuclear charge, then the ground state will become unstable against electron detachment. Now, for real physical systems, z can be considered only as integer numbers, but for this case, z has been considered as a real continuous variable, which triggers the notion of fractional nuclear charges. But it is an interesting field of research of study where ground state energy of a quantum system is varying analytically with z. In the year of 2014, Estin et al. Reported the most accurate value of Zc for a two-electron system. Moreover, they have also predicted that the outer electron among these two electrons will remain localized near the nucleus and even at Z equals to Zc. That means at the critical nuclear charge, the electrons will not be detached from the system, and it will remain localized near the nucleus. Not only that, they also proposed that the bound state changes smoothly into a shape resonance state for Z less than Zc. Later on, in the year of 2015, Jean-Philippe Corr confirmed this existence of shape resonance by estimating the uh, calculating the resonance width of the system for z less than zc, in which in this diagram he have shown that Jean-Philippe has shown that the resonance width is gradually decreasing with the increase of z, and at the critical nuclear charge it will become 0. That means for z less than zc there exists a shape resonance. So under these circumstances, we have made an approach to study the critical behavior of a ZEE system under the influence of exponential cosine screen Coulomb potential, where mu is the screening parameter, and it also represents the strength of the screening or range of the interaction. Basically, a three-body system under ECSC interaction is a major topic of research, as it has many applications in different branches of physics like nuclear physics, solid state physics, physics of dense plasma. Further in this project, we have also calculated the ZC values of the system for different mu values. We have also different structural properties along with two particle density for all possible orientation of the electrons have been estimated. And finally, we have reported quantum phase transition of the system around ZC values for different screening parameter by experiencing structural symmetry breaking in the structural parameters of the system. Now, let me give a brief outline of the methodology of this project. Here, it is the Hamiltonian of the JDE system under the influence of ECSC potential. And you can see here for mu equals to 0, this Hamiltonian will readily behave like a Hamiltonian of a pure Coulombian system. Not only that, the Hamiltonian is a function of continuous real variable z, and we have considered it as a parametric function of mu. And to find out the energy values, we have considered the wave function. Like this, and the wave function we have considered a multi-exponent Hilarius type wave function to incorporate the electron-electron correlation explicitly inside the wave function. Here, eta ij are the Slater type orbitals, where is the orbital index and j is the particle index. In the present calculation, we have considered multi-exponent basis set, and the nonlinear parameters rho in this expression are generated from a geometrical progression with GP ratio gamma. To obtain this lowest ground state energy, the gamma value is varied smoothly. Now, the energy eigenvalues are evaluated by repetitive diagonalization of the generalized eigenvalue equation. For this purpose, we have used ISPAC as the diagonalization subroutine, and all the calculations we have done in quadruple precision. And this is the generalized eigenvalue equation, where H is the Hamiltonian matrix, S is the overlap matrix, and C is the column matrix consisting the linear variational coefficient, and H is the eigenroots. So in the result section, we have estimated the ionization potential of the system using this expression, where E1s2 is the ground state energy of the JDE system, and E1s is the position of the first ionization threshold. And the first ionization threshold has been estimated by diagonalizing the Hamiltonian matrix of the one electron ZE subsystem, and we have used the wave function of the ZE subsystem, which is expanded in pure exponential basis set, where alpha I are the nonlinear parameters, and like the two electron system, these alpha values have also been generated from a geometrical progression, from a different geometrical progression. Now the estimated ionization potential values have been plotted with respect to mu for different z values from z equals to 1 to 0.6 in the interval of 0.01. As you can see here, the IP values gradually increases to a maximum and then decreases smoothly to 0, which indicates that under feeble screening the system gains more stability. That's why the IP value will become more positive if the mu, that means the interaction strength or the screening parameter, increases initially, and after that it will gradually decrease. Similarly, the estimated IP values have been plotted as a function of Z for different screening parameters. It is observed that the IP values are gradually decreasing with Z irrespective of mu value. But it is interesting to note that for mu less than 0.025 atomic unit, which is in the left hand side diagram, the IP values decreases more rapidly with Z, which causes crossing over between the lines. This indicates that the system possesses same stability or same IP value for a lower Z value in presence of screening up to the screening parameter 0.025 atomic unit. However, for mu greater than 0.25 atomic unit, IP value varies uniformly with Z. Not only that, the Z values for which the IP values decreases to 0 is referred as the critical nuclear charge of the system, as because for that particular Z value the IP value is 0, so the system will be destabilized. So we have estimated these Z values, that means ZC values corresponding to different mu values from graphical extrapolation from this graph. And in this diagram we have plotted the estimated critical nuclear charges with screening parameters. It shows that at mu equals to 0, if you look like in the diagram, at mu equals to 0, the ZC value is 0.9 or slightly greater than 0.9, which indicates that the minimum charge required in the nucleus to hold 2 electrons is less than 1. Further, it is fascinating to note that if the screening parameter, that means if the strength of the screening is gradually increases, then the corresponding nuclear charge, minimum nuclear charge to hold 2 electrons, will gradually decrease, and up to a certain value of mu, which is 0.25 atomic unit. After that means when, but for mu greater than 0.25, the ZC value increases almost linearly, and at mu equals to 0.7 atomic unit, ZC becomes 1, which suggests that ZC1 means, if you consider Z equals to 1, it means that it is hydrogen minus H minus ion. So in general, H minus ion is a stable system, but if the H minus ion is under the influence of ECSC potential, then at 0.7 atomic unit screening parameter value, this H minus ion will become destabilized. So this is an important conclusion we can draw here. Now next, let me discuss about the structural changes due to the change in the nuclear charge of the system under the influence of ECSC potential. To define the structural parameters, we may consider the JDE system as per the schematic diagram. where R1 and R2 represents the distance of the electrons from the nucleus, and R12 is the inter-electronic distance. Whereas the angle between R1 and R2 is referred as theta 12, and theta 1 is the angle between R1 and R12. Basically, we have estimated the expectation values of the structural parameters as a function of nuclear charge of the system using the optimized wave function. Uh, Now, if we just plot them with respect to z, as we have done here in this diagram, we have plotted the expectation values of the radial parameters, that is R1 and R12, for mu equals to 0.1 atomic unit. As an example, the radial expectation values remains almost same as z decreases below 1 up to a certain value. So it is very clear from this part of the diagram that it is almost consistent with the variation of z, but after a certain limiting value of z, it abruptly changes, and if we decrease the z value further, then the structural parameter abruptly changes, and as if the system diffuses suddenly beyond the limiting value of z. But it is interesting to note that the limiting value of z is close to the zc value of the system. Here I have mentioned the zc corresponding to the mu value 0.1 atomic unit, which is 0.84292. And that it is shown here that the region where this abruptness occur is at is around the zc value of the system. Similarly, we have plotted the angular expectation values of as a function of z for the same value of mu. Here also the expectation value of theta 1 and theta 2 changes abruptly around the critical nuclear charge, which is the same for the previous case, like this. So from these two diagrams, it is clear that the structural parameter changes abruptly around the zc value of the system, but what will be the fate of the electrons around the zc is not clearly understood here. That means what? Okay, thank you. To have the clear idea about the relative position of the electrons with respect to the nucleus, we have estimated the two particle density of the system, in which we will have, it will give us the information about the most probable configuration of the electron pair. And if we just for example, we have considered mu equals to 0.025 atomic unit. Corresponding to that, we have considered two different z values, z equals to 0.9 and z equals to 0.89, and we have calculated the two particle densities, which is a function of R1 and R2, and we have plotted these two. In this diagram, we have plotted rho as a function of R1, R2 in three-dimensional surface. In the left hand side, the diagram is for z equals to 0.9, and the other is for z equals to 0.89. For z equals to 9, a single peak have appeared for equal values of R1 and R2, and it have been noted that these two that the equidistant symmetrical position of the electrons from the nucleus is the most preferable configuration of the system, whereas for z equals to 0.89, two distinct peak occurs at two different set of R1 R2 value, and it has been noted that these coordinates of these two peaks are 60, 2 and 2, 60 respectively. These are in atomic unit, and this coordinates of the maximum suggest that the probability of the second electron to jump to a larger distance, that means since one electron is at 2 atomic unit distance and another electron is at 60 atomic unit distance, so the probability of the second electron to jump to a larger distance from the nucleus is maximum for z equals to 0.89. Now here comes the most interesting part of this, and that is the zc value, that means critical nuclear charge of the system for mu equals to 0.025 atomic unit is 0.9. So we can conclude that the critical nuclear charge of the system, at the critical nuclear charge of the system, since it is 0.9, so as we have observed here, at the nucleus, whereas the symmetrical configuration of the electrons is completely vanishes for z less than zc, that means z less than 0.9, which is clear evidence of quantum phase transition of the system. Now, to investigate the transition more precisely, we have estimated two particle densities in the intermediate points between z equals to 0.9 and z equals to 0.89, and arranged them sequentially to form this animation. So let me play the animation, just in which we can see how the peak gradually decreases from the symmetrical position, and the symmetry has been broken when the z value is less than zc. So this is all about the statement from our recent work. Now the conclusion part is that we have discussed elaborately about the critical stability of two electron system in a ground state under the influence of ECSC potential, and the electron-electron correlation have been explicitly considered by considering a Hillard's type basis set, and the ZC values of this system, that means two electron system under ECSC potential, have been predicted for the first time in this paper, and the expectation value of interparticle distances and angles have also been estimated for different mu values. We have just for brevity, I have shown you a few of the results, but for different mu values we have calculated these things, and the basic features of all these structures, all these figures will remain same as if we change the mu value, and the variation of structural properties and two particle density confirms quantum phase transition of the system around ZC. Just let me mention one thing here, that this critical nuclear charge and quantum phase transition was a analytical conjecture before, but just calculating the structural properties and the two particle density, we are able to understand how the electrons are changing their position, and by that way we can visualize that how the symmetry is broken, and by that way we have predicted the quantum phase transition of the system. So this is a completely new approach to see quantum phase transition. So all these results is published online in the journal, the European Physical Journal D, and it have been published on 12th October 2020. And thank you.
Okay. Now the paper is open for discussion.
Sir, I have a question.
Okay. Okay.
Uh, we are familiar with two electron system like hydrogen negative ion, whose
Yes.
nuclear charge is 1, and another is helium. Nuclear charge is 2. Please explain when nuclear charge like 0.97, 0.8, 0.958, when the charge nuclear charge is variable. Please explain.
No, as I have mentioned in the presentation in the previous slides, that this kind of systems, this is a just analytical approach to understand how the energy is varying with respect to Z. So that's why if you want a physical example, so it is not possible to give any physical example like this.
Okay, thank you.
Okay. One clarification I needed, that
Yes.
your from structural value variation configuration, you have pointed out the variation of theta versus z.
Yes. Yes.
Where the particular point up to which this is abruptly changed. Why it is so? You see,
Uh,
the curve you are giving that up to a certain level, it's okay.
yeah, that means
But
are you
after
talking
that,
about
that limiting point, why it is
Mhm.
going abruptly changes?
Okay, and that means in that case that I can say this in that the Hamiltonian of the system is consisting of the potential energy part, and in potential energy part we have two terms: the attractive part and the repulsive part of the potential energy. So
Yes, yes.
under this just in the under the influence of this potential having that mu value and
Mhm,
the z value, so these two parameters are playing a crucial role here. So for that particular
mhm,
combination of mu and z up to a
mhm.
critical value of z, the one part of the potential energy is dominating and other part is submitting, but the repulsive part is basically dominating after that one. That means when z is less than this one, so that's why this kind of abrupt increase in the, that means diffusion in the system occurs. So that is
Okay,
and
okay,
okay.
okay. If you have any other questions, since there is no questions, no more, I thank Dr. Anjan Saduka
Thank you.
for
Thank
his illuminating presentation, and I thank on the behalf of Netaji Nagar Day College. Thank you very much.
thank you, sir. Thank you. Thank you.
I now request the Sri Vishwajit Das, uh, PhD scholar, Department of Mathematics, Modern University, to present his paper. His title of the paper is Properties of Hydrogen Atoms in Dense Semi-Classical Hydrogen Plasma. Uh, Sri Das, please start
Yes.
here.
Is it audible?
Yes, yes.
Okay.
Okay, you can start.
Is it visible, sir? Sir, is it visible?
Yes, yes.
Okay. Good afternoon to everyone. I am Vishwajit Das, Junior Research Fellow, Department of Mathematics, the University of Burdwan. Now I am working under the supervision of Professor Ajit Ghoshal. Thanks
Okay.
to organizer, especially to my senior Sujay Kumar Nayak, who gave me an opportunity to present my work on this online webinar. Sorry, sir, it's technical problem. I arise. Okay.
Yes, yes.
Not showing. Okay.
No, your slide is not showing.
Is it visible, sir?
No, no.
Sujada? I have to open a window or your entire screen. Now present now there are three options. Your entire screen, a window, a Chrome tab. For a window. Okay. Okay.
Now it's showing. Okay,
Okay.
okay.
Thank you. Thank you. Now I am going to present my presentation entitled Properties of Hydrogen Atom in Dense Semi-Classical Hydrogen Plasma. These are the outlines of my presentation. Now I briefly discuss the motivation of this work. Properties of dense semi-classical plasma are of fundamental importance for studying astrophysical objects, inertial confinement fusion plasmas, and for setting up controlled nuclear fusion system. The word dense is characterized by the interparticle distances in plasma. In a dense plasma, the average interparticle distance is of order of the de Broglie wavelength lambda b of the charge carrier. It is thus necessary to take into account the quantum mechanical effects such as diffraction, symmetry, apart from collective effects such as skinning effects for the correct description of such plasmas. It is known that the effects of diffraction arising out of uncertainty principle cannot be neglected in the high temperature. Accurate calculation of various properties of plasma greatly relies on the description of uh, interparticle interaction in plasma. One way to describe the interparticle interaction is the use of pseudopotential or effective potential. Derivation of appropriate pseudopotential should take into account all the specific features of plasma, taking into account both collective effects at large distances and quantum mechanical effects of diffraction at short distances. Ramajanov and Agulova have derived a pseudopotential of particles interaction in semi-classical dense plasma by using a method based on the dielectric response functions. Using perturbative expansion, Dutos and Gombert arrived at the same pseudopotential while studying the diffraction correction in high temperature range for the pair correction function of one component classical electron gas with a neutralizing background. In this presentation, our object is to employ fully quantum mechanical treatments to investigate the properties of bound states of electron proton system like hydrogen atom in dense semi-classical hydrogen plasma. In particular, the investigation includes the stability of hydrogen atom for a wide range of plasma parameters. Special emphasis is made to compute accurately the critical values of plasma scattering parameters. Here, the pseudopotential giving the interaction between two unit charges of opposite kind separated at a distance r is given by the equation 1, where A and B used is given by equation 2, and kappa is the plasma scattering parameter whose reciprocal is the Debye radius Rd. The above pseudopotential remains real and gives correct description for 2k into lambda b less than 1, which holds good for the temperatures and densities that we consider in present paper. Sometimes two-dimensionless quantities, namely coupling parameter gamma and density parameter Rs, are used for the description of state of such plasma. These parameters are connected with the density and temperature of plasma. The coupling parameter represents the potential energy of interaction at the average distance A between the particles per unit thermal energy, that is gamma equal to E square by A into kb into T, where E is the electronic charge, kb is the Boltzmann constant, and A equal to 3 by 4 pi into n e whole to the 1/3. The density parameter Rs measures the average distance between particle in comparison to bore radius A0, where m is the electronic mass and h dagger is the reduced Planck constant. In terms of coupling parameter gamma and density parameter Rs, the de Broglie wavelength lambda b and dy length Rd are given by this. Note that when there is no skimming, that means K tends to 0, the pseudo potential given by 1 reduces to Dutow's potential given by the equation 3, which takes care the quantum mechanical effects of diffraction at small distances. Again, if we neglect the quantum mechanical effects, that means lambda b tends to 0, the pseudo potential reduces to familiar Debye-Hückel potential given by equation 4. That is 1 by r into e to the power minus kappa r. Now, briefly discuss the theory and calculation part of this work. In the center of mass coordinate, the non-relativistic Hamiltonian of the electron-proton system in dense semiclassical hydrogen plasma are given by the equation 5, where m is the reduced mass of the system and h0 is the kinetic energy of the relative motion and v is the potential energy operator. The bound state wave function phi r and corresponding energy, obviously negative energy, are determined within framework of Rayleigh-Ritz variational principle by employing the trial function given by 6, where ylm is the spherical harmonics, ci are the linear expansion coefficient, and alpha I and ni are the non-linear variational parameters. Details of the computational procedure are explained in our previous published paper, which are mentioned in references by 16, 17, and 18. Let H denote the non-relativistic Hamiltonian of the electron-proton system. Substituting of equation 6 in the Rayleigh quotient given by this, followed by optimizing of linear simultaneous equations given by the equation 7, where Hij and Sij are the Hamiltonian matrix elements and overlap matrix elements are given by the equation 8. In matrix notation, equation 7 can be written as the equation 9. The bound state energies are thus the negative eigenvalues of the N0 by N0 matrix S inverse H, which are computed by using QR algorithm after transforming the matrix to a Heisenberg form. Now we discuss the results. One of the fundamental issues relating to the potential governing electron-proton interaction is that whether the potential supports any bound state to the electron-proton system. Moreover, if it happens, how the bound states are affected by the plasma parameters kappa and lambda b. In this paper, we make an attempt to address those questions. In order to So we need to calculate the bound states energies quite accurately. We have employed an extensive trial function to calculate the bound states energies of hydrogen atom embedded in dense semiclassical hydrogen plasma by solving the corresponding Schrodinger equation within the framework of Rayleigh-Ritz variational principle. The trial function 6 has been expanded by choosing the nonlinear variational parameter alpha I ni as follows of the form. The above scheme of choice allows us to increase the number of terms in the trial function of 6, keeping the set of terms linearly independent. In table 1, using 150 numbers of terms in the trial function 6, we have been able to achieve accurate bound state energies convergent up to 11 places of decimal as shown in table 1 of hydrogen atom in dense semi-classical hydrogen plasma by using quadruple precision arithmetic. In this table 2, some binding energies of hydrogen atom are given. We see that the number of binding energy, ground state energies are finite. But in Coulomb potential, the number of ground state energy are infinite of hydrogen. In this figure, the ground state energy of hydrogen atom embedded in this plasma as a function of plasma scaling parameter kappa is put up in this figure for a number of de Broglie wavelength lambda b. From this figure, we note that for a given lambda b, effect of increasing kappa is lift the bound states towards the continuum. Bound states are also lifted towards the continuum when lambda b is increased at a given kappa. Thus, the increase is either lambda b or kappa leads hydrogen atom towards the instability. That means there are no bound state above this parameter. In next slide we will show the critical scaling parameter. In this table 3, we present the critical values of kappa and lambda b. The values of kappa and lambda b beyond which the electron proton in table 3 guides us the accurate information regarding the range of stability of hydrogen atom. In this table, we observe that with the increasing lambda b, the critical values of kappa decreases. On the other side, increase of kappa reduces the critical value of lambda b. However, we note that the electron proton system retains at least one bound state for the temperature and density lying in the range given by in this slide. Here we are actually recently in this work was published in Physics of Plasma, and the relation between lambda b and kappa with the temperature and density are shown in this published paper. Let me finish. The present study is an attempt to explore the features of the bound states of charged particle in dense semiclassical hydrogen plasma, wherein the particle interaction is described by the pseudo potential, which takes care of the collective effects at large distances and quantum mechanical effects of diffraction at short distances in plasma. The present study reveals that an increase in plasma scaling strength as well as the de Broglie wavelength takes the hydrogen atom towards instability. However, the atom remains stable. That means it is that is at least one bound state exists for the temperature and density lying in the range. We hope that our present study will provide useful information in the interpretation of kinetic properties of plasma and in studying astrophysical objects. These are the references. It's my pleasure to inform you that this work is published few days ago in Physics of Plasma, and it was selected as an editorial pick. Thank you.
Okay. Now the paper is open for discussion.
Hello? Hello, can you hear me, Vishwajit?
Yes.
Uh, Mr. Vishwajit, you have shown one of your slide that you choose the nonlinear parameter of your wave function in a particular way. Can you go to that slide?
Yes, yes. Yes. Is it
Okay.
visible?
Yes. I just want to understand how did you choose such nonlinear parameter? Can you just elaborate a little bit?
Okay. Actually, uh, in this beginning of my career, I will try with my supervisor tell me this how to expand the basis, and I try to in this way in the tree type way. Actually, if you when we choose ni equal to 0, alpha I are like point 1, point 9, point 8, point 7, point 6, point 5, and when ni then point 09, point 08 in this system, and it is uh, and I have to check
No, actually,
this
you are
basis is
using.
linearly independent or not.
Okay, so I think you used some optimization program, something like that, to choose that particular optimized nonlinear parameter, right?
Uh, I made a program which already optimizing this system,
Okay. Okay.
and I get a output which already optimized. And
Okay, I
when
understand. Okay.
yes, thank you.
Okay, if there is no other questions, I thank Mr. Vishwajit Dash for his presentation, and hope you will give some insight into this paper next.
Thank
Okay,
you, sir.
thank you. I now invite Srimati Aparajita Das, who is the PhD scholar, Department of Physics, Alia University, Newtown, Kolkata. His title of the paper is Control of Absorption, Transparency, and Amplification in a Microwave Driven Delta plus Lambda type close contoured interaction system. Srimati Das, please start here.
Okay. Am I audible?
Yes.
Okay. I'm presenting my screen. Good afternoon, everyone. Today I am going to present my our recent work on control of absorption, transparency, and amplification in a microwave-driven delta plus inverted delta type closed contour interaction system. This is the brief outline of my talk. First of all, I shall discuss what is the response of the atomic system to the electromagnetic fields. Then I shall introduce our system that we have chosen for our investigation. After that, I shall discuss a little bit on the dress states and dress state picture. And last, I shall conclude with the observation. So let us start with the first topic, response of the atomic system to the electromagnetic field. So what is response of the atomic system to electromagnetic field? Response means how an atomic medium responds to an electromagnetic field when when the system is irradiated by that field. If we have we have a electromagnetic field which we can call a probe field, because we are investigating the changes appearing in the system by this field, and we are considering that the circular frequency of that probing field is slightly detuned to the transition frequency between these two electric dipole allowed transitions. So if we plot the absorption coefficient of that probing field with respect to the probe detuning, we get a Lorentzian absorption profile with maximum absorption when the detuning is 0. That means at resonance. Next, we are shining this atomic system with another electromagnetic field, which we can call a palm field. This field is resonant to the transition between these two states, provided that this state 1 and this state 3, they are electric dipole transition forbidden states, but magnetic dipole allowed transitions may occur in between these two states. So it is predictable that the absorption profile will be similar to the previous Lorentzian absorption profile. But interestingly, this probe field in presence of another electromagnetic field is not absorbed at all by the system. That means the medium becomes transparent to this field. This transparency is induced in presence of another electromagnetic field. That is why this phenomena is called electromagnetically induced transparency. In this situation, if we shine the atomic system with another electromagnetic field that can couple these magnetic dipole allowed states, and if we plot the probe absorption coefficient with respect to this probe detuning, we get a surprising result. What we get? We get a probe absorption with the amplification of probe simultaneously at different detuning positions or different probe frequencies. So at that point, it is clear to us that we can control the responses of the atomic system or atomic medium to any electromagnetic field if we shine that system with other electromagnetic fields. Motivated with this, we have chosen an N-type atomic system, atom laser coupling scheme, prepared with the hyperfine energy levels of rubidium-87 atoms. P1 and P2 are the external pumping fields, and this is the probe field that connects hyperfine level F equals to 2 to hyperfine level F double dash equals to 2. And these transitions are all our electric dipole allowed transitions, and we can drive all these transitions by a laser field of wavelength 780 nanometer. Now, if you see the energy separations between the ground hyperfine levels as well as these excited hyperfine levels, these frequencies are matching with the frequencies of microwave or radio frequency fields. So we can couple these states these two ground state as well as these two excited states by two microwave fields. And as these states are not electric dipole allowed states, but magnetic dipole allowed transitions are possible between these two states. So we have to use the magnetic field component of the microwave field. We designate this field as lower coupling field or L, and this is the upper coupling field. We designate this field by U. So the main aim of our work is to control the responses of the system to the probe. So we have to find out some controlling parameter. One obvious controlling parameter must be the intensity of the incident electromagnetic field, which we can easily control externally. Another controlling parameter may be the relative phase between the three fields, because a microwave field, a probe field, and another pump field produces a closed interaction contour system. So what will be the relative phase? We can calculate the relative phase by adding the phase parts of this probe and microwave field, and then subtracting this phase part of the pump field, and ultimately we get the relative phase in this form. Here these phase parts, omega, PRT, K, PRZ, or these parts are not included here because they all are cancelled out. And if we consider that the transitions are driven by a single laser, the pump and probe field, if you consider that the pump and probe fields are prepared from the single source, so the initial phases of these fields will be same. So these will also be cancelled out, and ultimately we can say that the phases associated with the microwave fields are equivalent or equal to the relative phases of these three fields. Phi 1 is phi 1 corresponds to the relative phase for the delta system of our delta plus inverted delta system, and phi 2 corresponds to the relative phase or the microwave phase associated with the upper coupling field for the inverted delta system. So to analyze the probe absorption profile of this delta plus inverted delta type system, we have used the density matrix approach and solved the optical block equations, and have plotted the imaginary part of the density matrix corresponding to the probe transition as a function of probe detuning. As by this formula, we can easily see that the absorption coefficient is proportional to this imaginary part of the density matrix rho 2 element rho 2 3. To understand different features in the probe absorption profile, we have also presented the dress state picture of the system. So what is dress state, or how we can obtain the dress state picture? We can follow the following methodology. We have a bare atom Hamiltonian, which is given by this. As the pump and probe transitions are driven by the electric field component of the incident electromagnetic field, so the this PR, EP2, and EP1 are the electric field component of those fields. And as we are coupling the lower ground hyperfine levels and excited hyperfine levels by the magnetic field of the incident microwave field, so we should consider the magnetic field components of the microwave field. Now, when the atoms, the system is kept in the electromagnetic radiation, they will interact with the field, and the interaction Hamiltonian, thus we can write in this form. We can write in the interaction Hamiltonian in this form as these rubidium atoms are or any alkali atoms are hydrogen-like atom, and they can be treated as electric or magnetic dipoles. And when they are placed in the electromagnetic field, they will quickly align towards the field direction, and we get the magnetic or electric dipoles, and we can define the corresponding matrix elements by this, where I and j runs from 1 to 4. Now, our total Hamiltonian, the sum of these two Hamiltonians, doesn't contain any frequency term or any time dependent term. But we all know that when a dipole is placed in the electromagnetic field, it will oscillate, and it will radiate, and we get some absorption or some transmission. So we have to include the time dependent or the frequency parts in the total Hamiltonian. For this purpose, it is very useful to transform the interaction Hamiltonian into the interaction picture of the bare atom system by a time evolution operator given by this, and then retransforming that Hamiltonian to the Schrodinger picture by this relation, and then adding the bare atom Hamiltonian and this HI interaction Hamiltonian, we get the total Hamiltonian, which becomes dependent on time. Now we have to further transform that H, that Hamiltonian, into a co-rotating Hamiltonian by an unitary matrix. That unitary matrix satisfies this relation. I'm not showing all the detailed steps, and finally going to the total Hamiltonian, the expression of the total Hamiltonian. Here you can see that all the field detunings have been included, as well as the pi parts, the phase parts of the microwave fields are also included. And these omega p or omega p1, omega p2, these are the Rabi frequencies corresponding to the probe field and the palm field. And this omega L and omega U are the magnetic field related Rabi frequencies for the microwave fields. This this Rabi frequency actually defines the strength of the incident magnetic field. Now we have to solve this characteristic equation where H is this, and then from here we get the eigenvalues. These eigenvalues represent the absorption peak positions, and the eigenstates define the Dress states, and we designate those Dress states as plus and minus. Plus state is for the symmetric superposition of the pair states connected by the dressing field, and the minus Dress state is the antisymmetric superposition of the same. Now it is clear that the probe is now connecting a bare state to a Dress state. So the corresponding Rabi frequencies that are connecting these states will also change, and we can get the modified Rabi frequencies, probe Rabi frequencies, by this simple symmetry transformation, where S is prepared by these eigenstates obtained from this equation. Now, what are the observation of our work? We have investigated the whole. We have separated our investigation into two parts, where first of all we have investigated the effect of field strength, and on the second part we have investigated the effect of the relative phase on the probe absorption profile. And for both the cases, we have also considered two separate cases when the second pump, for the first case, the second pump is stronger than the first one, and the latter one is when the first pump is stronger than the second pump. Similarly, for relative phase effect, to see the effect of relative phase, we have also considered these two cases. So, what is the effect of field strengths on the probe absorption profile? Here, this is the total Dress state picture of our system when all the fields are on. And in the right hand side, you can see the probe absorption profiles for when we switch on all the fields one by one. First of all, when all the pumps and coupling fields are off and only probe is present, we get a simple absorption profile at zero detuning for obvious reasons. Now we are switching on the second pump P2, which acts as the dressing field for this case 1, and it produces the two dress states plus and minus. Now as soon as we switch on this second pump, this single absorption peak splits into two absorption peaks, and these peak positions are giving the dress state positions with respect to the zero detuning. Next, we are switching on the second pump. For this case, the P1 that connects where state 1, 2, 3. Here we can see that this yellow peak for both the detuning positions are further split into two peaks. This profile is similar to the probe absorption profile corresponding to a 3-level system that I have discussed initially. So what are the 3 levels that are contributing in producing this kind of profile? So the 3 levels are here 1, 3 and minus for this profile, and state 1, state 3 and plus for this profile. Now we are switching on the lower coupling field. Here we can see that these symmetric absorption peaks are getting changed. We get an asymmetric absorption peak pairs in both the detuning positions. We can say the reason behind this is asymmetric absorption peak in terms of this rested picture, where for this case, these two asymmetric absorption peaks are produced due to the competition between two different absorption channels. First one is this 1, 2, 3, that is the direct absorption channel, and the other is 1, 2, minus 2, 3, that is an indirect absorption channel for this profile. And for this profile, the direct channel is the same 1, 2, 3, and the indirect channel is 1 to plus and then to 3. Now we are switching off that lower coupling field and switching on the upper coupling field. We get here this violet profile. Here the profiles in both the detuning positions for the dress states, they are similar to the 3-level systems, as there is no direct or indirect channels, only they are similar to the 3-level systems. So the 3 levels are 1, 3 and this plus and minus, but the overall absorptions are not same for both the detuning positions. We can say that this happens due to the non-equal strength of this effective Rabi frequencies. When the okay, then we are switching on all the fields and we get this red curve. This red profile is similar to this blue profile. From this we can infer that when all the fields, all the pump, probe, and the microwave fields are on, the lower coupling field dominates over the upper coupling field. For the second case, when the dressing field is the first pump P1, we obtain similar kind of absorption profiles, but the main difference is this YOLO curve. In the previous picture, in the previous plot, we saw that the absorption is very less at that two detuning positions, but this for this case the absorption is quite high, because here all the two ground states are participating in this absorption process. As they are rich in population, we obviously get a good amount of absorption. Other profiles are similar, so I am not discussing, only I am mentioning that here, interestingly, the upper coupling field dominates over the lower coupling field when all the fields are kept on. Now, what is the effect of microwave field phase on the probe absorption profile? For the first case, when the second pump P2 is stronger than P1, we have plotted a contoured plot for the variation of imaginary part of row 2, 3 with varying both the phases phi 1 and phi 2 for two detuning positions where the states are produced. Here you can see that this elliptical shaped or the elliptical shaped blue as well as these yellow portions are changing periodically with respect to phi 1 as well as phi 2 for both the detuning positions. And this deep blue portion has a negative value. That means in some combination, for some combinations of phi 1 and phi 2, we can get some probe gain. And these yellow portions are for positive values of row 2, 3. That means here we are getting absorption, and these light blue portions are indicating the transparency. So it is to be noted that the observation of simultaneous absorption and transmission can be used to produce the simultaneous flow or fast light in the medium by this by such atomic system. For the second case, when the first pump, that means P1, is stronger than P2, we have also plotted a contour plot for the variation of imaginary part of row 2, 3 with respect to both phi 1 and phi 2 for both the detuning positions. Here also we get some periodic yellow and blue elliptical regions, but here you can see that this deep blue portion is not negative, it is positive. That means here for the second case, when the dressing field is P1, we are not getting any kind of probe gain. We only get absorption or transparency. They can be changed periodically by the suitable combination of phi 1 and phi 2. So by switching both the coupling fields on and by periodically changing phases with same values, we can control the degree of absorption for this case. These are some other observations that we have observed, and I'm just telling only the important observations. A delta type subsystem with P2 pump, second pump, for when that P2 is the dressing field, is equivalent to the inverted delta type subsystem with P1 for omega P1 greater than P2. That means when P1 is the main dressing field, and this is vice versa. Another thing is we have not shown all the dephasing terms or the decay terms in the diagram, but they are still present in the medium, and they can also affect the coherences between the two ground states as well as the two excited states. So the spectral profiles in one case, say when P1 is greater than P2, can be predicted for predicted from the other one. That means when P2 is greater than P2, by controlling the dephasing or and the non-radiative decay rates that are present in the medium, and by changing the relative phases between the three fields. And these kind of systems, this lambda, this delta plus inverted delta type system can be used for optical switch or slow fast or fast light generation for experimental as well as different applications of uh, quantum optics. Thank you.
Okay. Now the paper is open for discussion. If you have any question, you can ask the speaker. Actually, one thing I just clarify it, that you have done your experiment, your experimental result and the theoretical results both
No, we have investigated only theoretically.
theoretically.
Hmm.
Achha. So how you are, when you are doing this experimental experiment, then how you can collect the data or you manufacture the data?
Well, by
When you do the when you do the experimental things, then how you get that data?
We should use a laser. We shine a say rubidium atomic shell and shine them with a probe, and we can produce the probe and pump field from a single laser source, and shine them the atomic that rubidium paper shell can be shined by them, and for that microwave fields we have to do some arrangement, because that magnetic field is very small. Magnetic field component of the microwave field or any electromagnetic field is very small compared to the electric field component. So we have to amplify that. So we have to place the rubidium vapor shell within a cavity, and then by amplifying that magnetic field, that amplitude, we can couple those tapes.
Okay. Okay. Since there is no other questions, I thank Srimati Aparajita Das for his fruitful presentation. Hope we will do. Hope that we will have the similar type of seminar to have and meet with you. Thank you very much. So
thank you,
now I
Aparajita.
am.
Thank you.
Now I am handed over the mic to Shujoy.
Thank you, sir. Before going to vote of thanks, we would like to know the experiences about this webinar, actually about this 2 days journey from our 2 and 3 participants. Please.
Okay.
You can share your ideas.
So we request our participants to interact what type of interaction have been done by you with the speakers and how you feel this. Please give your experience in our.
Dr. Kaushik Ghosh is with us. Sir,
Okay.
please share your comments about this webinar. Dr. Kaushik Ghosh from University Institute of Technology, Burdwan. No, I think.
Dr. Devnath, if you
Am I
have.
audible?
Yes, audible.
Okay.
Yes.
Actually, the audio in
Okay.
my laptop was not working. That's why I switched to
Okay.
mobile device. Yeah, thank you very much for giving me the opportunity to say something in the valedictory session. It was a very nice experience throughout 2 days, and I learned a lot, especially like today in the morning session. That harmonic oscillator, that talk was a very nice one. From the very preliminary ideas. And then he proceed to the quantum aspect of this harmonic oscillator. That was very nice. And I also watched all these 4 lectures of some research associates and research scholars, and very inspiring. They're working in the good aspects of these particular fields, and perhaps all of them have published good articles in different reputed journals. So my best wishes to all of them. And again, thanks to organizers for organizing such a wonderful webinar in this particular fighting time in this period. And I just request to the organizers, if possible in future, if you can arrange this particular conference in a broader aspect, that means some more topics and some more particular contributed presentations can be included. That will be better perhaps. Thank you.
Thank you, sir. Thank you for your valuable comments. We shall keep you in mind your words and shall try to do best in the next webinars. Thank you, sir.
Thank you. Thank you very much. Thank you, Shuja, and everyone.
Jayantada, Dr. Jayanta Saha, Assistant Professor, Department of Physics, Alia University. Dada,
Yeah, thank you. Thank you, Shujoy, and organizer for organizing such an excellent seminar. I have few observations. Like, it is a very nicely poised webinar, because the first day it is all about the experiments, and the second day it was all about the theory. So nothing good. I mean, if we have a good amount of theoretician and the experimentalist. In fact, we have discussed one of the state-of-the-art techniques that are doing worldwide as well as in India in TIFR. And also in different parts of the country, people are joining in this seminar. What I find that the number of participants are less. Shujoy told me that the total registered participants will be around 200. But somehow
279.
279. So it is very unfortunate. It is very one of the reason, maybe it is going to the festive season, because when I was in postdoc at ISES, so what I find that a workshop, it was a very fruitful workshop that has been organized in ISES in 2015, I think, and only it was 12 or 13 participants, including me, that has been joined in that workshop. I mean, after getting so many phone calls, people are not participating. So in that, considering that in mind, 40 or 40 odd people are good. But maybe in future we can arrange more peoples. And also it is right that if we can consider short talks but more number of participants from different parts of Bengal and the national or international. So thank you very much, and keep organizing such seminars. All the very best users.
Thank you. Thank you, Doc. Thank you very much for your valuable comments. Or any other person? I would like to know experiences from the research scholars. Okay, thank you. So now the time for vote of thanks. I would like to invite Dr. Bornali Datta, Assistant Professor of Department of Mathematics and Head of the Department, to deliver vote of thanks. Dr. Datta.
Good afternoon, everyone. I feel that it is a great honor and privilege to propose the vote of thanks on this memorable occasion. On behalf of the organizing committee of this international webinar on mathematical theory of atoms and molecules, I would first like to express my sincere gratitude to all the three invited speakers, Professor Lokesh Trivedi, Professor Shapun Mondal, and Dr. Shubhadeep Bishwas for delivering wonderful lectures and sparing valuable time from their busy schedule for this webinar. They have agreed to present their talks at short notice. Thank you very much, sir. Special thanks to Dr. Abhijit Majumdar, Honorable President of the governing body, Netaji Nagar Day College. Yesterday, sir had joined in the inaugural session of this program. Sir had always been encouraging us to organize such type of program. Thank you, sir. My heartfelt thanks to our principal madam, Dr. Sonali Banerjee Josh, for her words of encouragement. Her able guidance has always encouraged us. I thank her for her kindness, her her interest and continuous support. We also would like to acknowledge our gratitude to all the research scholars who have presented their papers in this webinar, Dr. Tanoy Devnath, Sri Anjan Sadhuka, Sri Vishwajit Das, and Miss Aparajita Das. Wish you all a great success in your near future. I am also thanking Dr. Chanchal Guhorai, IQAC coordinator of Netaji Nagar Day College, for nicely conducting the technical session as a chairperson. I would like to thank all the participants. Thank you for your active participation and inputs. I must mention our deep sense of appreciation for our colleagues in our college. Thank you all for your moral support to make this event successful. I would like to thank all of my departmental colleagues, Dr. Chanchal Guhorai, Dr. Ujjwal Kumar Pahari, Mr. Pitambar Das, for their continuous support to make this webinar successful. Last but not the least, I would like to extend our thankful gratitude towards our departmental colleague, Dr. Sujay Kumar Naik, for his tireless effort as the convener for this webinar. Thank you.
Thank you very much, Bornali. So I think I would like to request Chanchalda to announce the session closed. Chanchalda.
Okay. Now, from the behalf of Netaji Nagar Day College, we now close our international seminar on mathematical theory of atoms and molecules. Thank you all.
Thank you. Thank you, everyone.
সুজয় আমরা কি একটা নিতাম ফটো নিতাম
Oh, photo.
নিয়ে নাও
Okay, okay. Please, participant request করবো একটু একটু ক্যামেরাটা অন করতে. I am requesting to all the participants, please turn on your camera. We shall take a picture.
ফিরে তোমাকেই তো দেখা যাচ্ছে না।
দু তিনটে নিয়ে নাও।
হুম, এইটা
আচ্ছা,
হ্যাঁ।